Okay, now we're going to talk about 3 theorems that will help you precisely graph instead of just sketching. Hone in on where you actually would graph these functions. So the first theorem that I want to talk about is the fundamental theorem of algebra, and this is probably the easiest one that we're going to work with. So it identifies, using that theorem, we can quickly identify at a glance the total number of roots. And when we say complex roots, what we're talking about is remember the roots are where a graph will touch. These are called roots or zeros because the height of the y value, right? If this is 1, this is -1, the height is 0. These are often called the zeros or the roots, all right? So the fundamental theorem of algebra says if you look at the exponent with the highest degree, or the x value with the highest degree, that's how many complex roots there will be. Easy. But complex roots can be real or imaginary. Think about when you have a quadratic, and let's say you have 2 plus or minus, and this ended up being the square root of, say, -6, which is -1 times 6. But the square root of -1 is positive or negative I. Well, I is imaginary, and it comes in pairs, positive or negative. So sometimes functions will have imaginary roots. The complex roots have to add up to 3, so they can be real or imaginary. So you take this real, the real will always follow the imaginary. But because imaginary come in pairs, count down by 2, so 3 subtract 2 is 1. So there's either going to be 3 real roots, and 3 real roots would look like this, or there could be 1 real root, and maybe that graph would look like this. Only one place where that graph touches the x-axis. So that would be 1 real root. The imaginary and the real have to add up to 3. So 3 plus 0, if there are 3 real roots, then there isn't any room for imaginary roots. But if there's 1 real, that means 2 imaginary roots. All right, so I'm going to clear all that. That's the fundamental theorem of algebra right there. That theorem. Well, I think it goes on to other things, but for what we're going to be using it for, you look at the highest degree, and that's how many roots there will be. For the real, you put exactly the same numbers complex, and then you subtract 2. Now, let's say you had 2x to the 7th. Well, for the real, so for complex, there would be 7. For real, there would be 7, subtract 2, 5, subtract 2, subtract 2. If you subtract 2 again, you're at -1, so you never go lower than 0. All right, so now we're going to go on to the next theorem. Same problem. So we've done all of this stuff, right? But now we have this theorem called Descartes' rule of sign, and what it does is it has us count when the sign changes from positive to negative. That will help us find possible positive reals, not imaginary, and possible negative reals. That's what Descartes was also a famous philosopher, and I think he actually dabbled in some art too. All right, so this is what you're going to do to start off with to check for possible positive reals. You look at the original sign, so that's a positive 2x cubed, a positive x squared, a negative 2x, a negative, and then you look at where it changes from positive to negative, or from negative to positive. Well, only one place, right there, from here to here. So there would be, let me do this. So for possible positive reals, there's only a possibility of one positive root. So let me erase all this. Now the next tricky part, and this is where some people get confused, so stay with me. Now we're going to check for possible negative reals. So if you replace the negative sign, so if we put 2 negative x cubed, and I'm just going to put a negative in there, plus negative squared minus 2 times negative, subtract 1. Well, that subtract 1, there's nothing that's going to change that, so that negative sign will stay. But look at what happens. When you put any negative number, say negative 1, into a calculator and you cube it, well, negative 1 times negative 1, well, that's going to be positive 1. And then when you take positive 1 and you multiply it by negative 1, that ends up being negative again. So when you take a negative number and you cube it, it ends up being negative. Well, this negative times this positive is a negative. Negative times positive is negative. So look what just happened. This started off as positive 2, but because the negative cubed is negative, negative times positive is negative. Now this next one, it's starting out as positive, but what's a negative number squared? What's a negative times a negative? Positive. Well, a positive times positive, that positive stays the same. That even exponent, that sign didn't change. That odd exponent, the sign did the opposite. Now we have an x to the first, an odd exponent again. Well, when you put a negative in there, that becomes negative. Well, this negative times this negative, oh, look it, that sign did the opposite. So each time there's an odd exponent, the sign in front switches. So this was x cubed, it switched from positive to negative. This was x to the first, it changed from negative to positive. So let's come down here. Let me erase all of this so you can actually see what happened then. So this was positive, this was positive, this was negative, this was negative. And on the odd exponents, the signs in front changed. So that was an odd exponent, it changed. An even exponent, it stayed the same. An odd exponent, it changed. The sign in front of the constant will never change. And now look. From here to here, it changed from negative to positive. And from here to here, it changed from positive to negative. So it changed twice. But remember, because of imaginary roots, we have to count down by 0. All right, so that is Descartes' rule of sign. All right, now we're going to go on to the rational root theorem. So the rational root theorem, so we did all that stuff, the fundamental theorem, we did Descartes' rule of sign, and now we're going to do the rational root theorem. And what it says is, you're going to take factors of the constant, so here's the constant, your positive and negative factors, that's very important, of the constant, and you're going to divide it by both positive and negative factors of, here is your lead coefficient, meaning your highest degree variable with the highest exponent, the coefficient in front, that's called the lead coefficient. So in this case, positive and negative factors of 1 are just positive, negative 1. Factors of 2 are positive, negative 2. And then what you're going to do is you're going to create this list. So 1 divide negative 1 is negative 1. 1 divide negative 2 is negative 1/2. 1 divide positive 1 is 1. 1 divide positive 2 is positive 1/2. And then if you said that this is negative, well, negative divide negative is positive. Negative divide negative is positive. Negative divide positive, you're back to the negatives. So out of negative infinity to positive infinity, those are all the numbers that we normally could try here we've narrowed it to 4 rational possibilities. So of the up here, remember there was either going to be 3 or 1 real and either 0 or 2 imaginary. So of the real, instead of an infinite number to choose from, we've narrowed it down to only 4 possibilities that will actually work as roots. So now you're going to do synthetic division. All right, so let's see. There is a possibility of 1 positive. I always like to start with positive 1 just because. So we're going to multiply, remember? So 1 times 2 is 2. Then add the columns. Add to 3. 1 times 3 is 3. When you add 3 to negative 2, you get positive 1. 1 times positive 1 is 1. When you add 1 and its opposite, you zero out. Ta-da! 1 is a root. By the way, you could actually use that number again if you wanted. Now here's the cool thing about synthetic division. We don't have to erase all this and then start again. We can now keep going with these numbers. So look at, positive 1 worked. So now this possible positive real, we have it. So we don't even have to check positive 1/2. We can focus on the negative numbers now. So I'll try negative 1. So negative 1 times 2 is negative 2. 3 plus negative 2, or 3 subtract 2 is 1. Negative 1 times 1 is negative 1. And negative 1 plus its opposite, or additive inverse, is 0. So x equals negative 1. Let me get rid of that. Wow, remember there were 3 possibilities. We're already at 2 of the 3. Well, what zeroes out positive 1 is negative 1. So the only way we can get to negative 1 is if we multiply 2 by negative 1/2. So negative 1, negative 1/2, and positive 1 are our answers. Now, I'm going to show you what that would look like graphically. Because now we have a much more, remember the previous video, I said the general sketch, all you would know, if this is negative 1, you'd know to put a solid dot here, and then the graph, I don't know, could be all over the place. But now we have some more information. We know it's the graph is going to touch there at positive 1. We know the graph is going to touch there at negative 1. And the graph is going to touch there at negative 1/2. Wow, way more specific now. We know the general graph looks like this. Well, now we have points to bring it down to. So maybe it looks something like this. Much more specific than that previous graph. All right, that is it for the video instruction for this week. And these were the 3 theorems to help you get more precise with graphing polynomials.